Hi there. So this is the second part of entropy. Now we're going to look at entropy changes in the system. Okay. So the standard entropy of reaction, which is delta S naught reaction, is the entropy change that occurs when all reactants and products are in their standard states. So if you want to find out delta S naught for a reaction, meaning at the standard conditions, what is the entropy change for a reaction, we're going to follow this formula where it says the sum of all the entropy values for the products minus the sum of all the entropy values for the reactants at their standard state. Okay. So here M and N represent the number of moles of products and reactants given by the coefficients in the balanced equation. Predicting the sign of delta S naught for a reaction. Sometimes we will be given whether a reaction delta S is positive or negative, but also by looking at a reaction we can predict whether delta S is positive or negative. Okay. Delta S naught reaction is positive, meaning greater than 0, if the amount of gas increases. For example, let's say here 1 mole of hydrogen gas plus 1 mole of iodine, which is solid, giving us 2 moles of hydrogen iodide. Now we have to look at the amount of gas increase. Now this is a solid, so we don't count the solid. Here you have 1 mole of gas giving us 2 moles of hydrogen iodide. So 1 becoming 2, meaning it increases the number of particles, which in turn increase the entropy, which is positive. Delta S naught reaction is negative if the amount of gas decreases. So we can use this example. It's not given here. You can consider nitrogen gas plus hydrogen, 3 hydrogen molecule. This is the process of making ammonia, giving you 2 ammonia gases. What do you think about the entropy of this one? Again, all 3 are gases. So we have to look at how many gas particles, how many gas molecules in the reactants and how many in the product. So 1 plus 3 is 4, giving you 2. What happened? Entropy decreasing. 4 moles becoming 2. Entropy decreases. So delta S would be negative by looking at the number of gas particles. And delta S naught is likely to be positive if a new structure forms that has more freedom of motion. Now you hear this is cyclopropane. There are 3 carbons. It's a cyclic compound. And then the bond angle is about 60 degrees. And this is very, excuse me. This is a very strained molecule. When you heat it up, it would break one of those bonds and make a double bond. Now it is more open. And it has a more degree of motion compared to the restricted cyclic form. So that increases the entropy of the molecule. So delta S naught would be positive. Okay, calculate the standard entropy of reaction delta S naught. Predict the sign of delta S naught and calculate its value for the combustion of 1 mole of propane. We can predict it before we start calculating. Let's go ahead and check to see if this is balanced. Yes, so 5 oxygen, 3, 4. This is a balanced equation. So gas, 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 liquid. Let's see. Here we have 1 mole of gas plus 5, 6 moles of gas becoming 3 moles of carbon dioxide and 4 water molecules. If you look at the gas particles, number of moles of gases, 6 become 3. Has the number of moles increased or decreased? Obviously decreased. So what happened to the entropy then? Should become decreased. If the entropy is decreased, what do you think? Delta S naught reaction, positive or negative? we can predict that it would be negative, right? So from the change in the number of moles of gas, 6 going to 3, the entropy should decrease, less than 0. So to find out the delta S naught reaction, we are asked to calculate what is the entropy for the reaction. We have to apply equation 20.4 using the standard entropy values from Appendix B. So this is the equation that we are going to use. We're going to use this equation. Delta S naught reaction equals sum of all the entropy values for the products minus the sum of all the entropy values for the reactants. Normally, if you are given a problem like this, you should be given the standard entropy values of these individual molecules. And then you add up the standard entropy values for your products, taking into consideration the number of moles, and then subtract the sum of delta S values for the reactants. So our products are carbon dioxide and water. There are 3 moles carbon dioxide times the entropy of the carbon dioxide plus 4 moles of water times the entropy of the water. Subtract the reactants. So 1 mole of propane times the entropy of propane. 5 moles of oxygen times the entropy of the oxygen. So the entropy value should be given to you. So these are the values. 3 times 213.7. 4 times 69.9. So likewise, and also we want to make sure all the values should be in the same units, joules per Kelvin per moles, all of these. If any of these are in kilojoules, then you have to convert them into appropriate units. Okay. So when you do this calculation, the answer is negative 374. And we also predicted that the delta S naught should be negative based on the number of moles, right? 6 becoming 3. So again, the real value also gave us a negative number. That's how you would calculate delta S naught of a reaction if you are given the standard entropy values for the individual molecules. Excuse me. Entropy changes in the surroundings. A decrease in the entropy of the system. Let's say you have a system and the entropy decreases, is outweighed by an increase in the entropy of the surroundings. The surroundings function as a heat source or heat sink. Excuse me. Excuse me. Excuse me. In an exothermic process. What is exothermic process? It releases heat to the surrounding. The surrounding then absorbs the heat released by the system, and the S surrounding increases. So the surrounding is getting entropy. Not the entropy, sorry, surrounding is getting the heat. Remember, as the temperature increases, we said the entropy increases, so the surrounding entropy increases if it is an exothermic process. Okay, so the Q system, because if it is an exothermic process, it releases heat, so the system loses heat. So Q system would be less than 0, right, because it is losing heat. And the surrounding, Q surrounding, increases because the surrounding is the one who is going to absorb that heat. It's going to be positive, greater than 0. And the surrounding delta S as a result will be greater than 0, positive. For an in an endothermic process, heat absorbed by the system and the surrounding loses heat. The surrounding provides the heat absorbed by the system, so the surrounding decreases the entropy. Q system, if it is an endothermic process, absorb heat, it would become positive. Q surrounding would be less than 0, negative, and as a result delta S surrounding also be less than 0. Temperature at which heat is transferred. Since entropy depends on temperature, delta S naught surrounding is also affected by the temperature at which heat is transferred. For any reaction, we can say Q system equals negative Q of the surrounding, because if the system loses a certain amount of heat, surrounding is going to absorb the same amount of heat and vice versa. The heat transferred is specific for the reaction and is the same regardless of the temperature of the surroundings. Okay, the impact on the surroundings is larger when the surroundings are at lower temperature, because there is a greater relative change in entropy of the surrounding. If the surrounding has a lower temperature, so the impact of the surrounding is going to be larger because there's going to be a bigger change. So we can calculate the delta S of the surrounding using this equation. Excuse me. Negative Q system, meaning the heat of the system, negative value, you divide it by the temperature. That will give us the delta S surrounding. Okay? And if the process is happening at a constant pressure, your Q, heat, and delta H are the same. So then the delta S surrounding would be again negative delta H system over temperature. So we can use this equation to calculate if you want to find out the delta S surrounding or the delta H or the temperature. So we can use this equation. Excuse me. And this is the temperature at which the heat is transferred. Excuse me. Determining reaction spontaneity. At 298 Kelvin, the formation of ammonia has a negative delta S naught system. So we are given the entropy of the system. Excuse me. So here the formation of ammonia. And also if you predict the entropy, here you have 1 mole nitrogen, 3 moles hydrogen, 4 going to 2 moles ammonia. So 4 becoming 2, entropy should be negative. So again the number also given as negative 197. Do you see that? Okay. We want to calculate the delta S naught of the universe and state whether the reaction occurs spontaneously at this temperature. Okay. Entropy was given negative 197. We want to see whether this reaction is spontaneous at this temperature. Plan for the reaction to occur spontaneously. Right? What happened? Entropy of this universe, entropy of the universe should greater than 0 for the reaction to occur spontaneously. Right? The universe should have more entropy greater than 0. So delta S naught surrounding must be greater than positive 197. Okay. So the universe represent both the surrounding plus the system. And the system is negative 197. If the delta S universe needed to be positive, delta S surrounding must be greater than 197. If it is exactly 197 and the system 197, it would become 0. If this is negative number, negative become negative. So this has to be more positive than 197. We need delta H naught system. We need to find out the delta H of the system, which is the same as delta H naught reaction. So we use the standard enthalpy value from appendix B to calculate this value. So basically we are going to use this equation. Delta S surrounding equals delta H system over temperature. Okay. And we are going to find out the delta H. It's the same thing I was going to show you over here. This equation. Delta H system. How do we find the delta H? Reaction. Again, it's the same. It is the same process as you would calculate, no, where's the pen? Trying to get the pen. Okay. Delta H also you can find out. Delta H for a reaction also is the sum of all the delta H values for the products minus the sum of all the delta H values for the reactants, standard enthalpies. Okay, just like we calculated the entropy, standard entropy for the reaction, we can do the same thing for the enthalpy. We did this in fact in our Chem 1. Now delta H reaction. There were 2 moles of ammonia. Ammonia is the product, right? Enthalpy of formation for ammonia times 2. These values, ammonia, nitrogen, hydrogen, enthalpy of formation, we can find from the appendix. Also in a problem you will be given these values. Okay, so formation for ammonia negative 45.9 times 2. Nitrogen, it's a gas, 0. Again hydrogen, also a gas, it is also 0. Okay, so basically 2 times negative 45.9. So the enthalpy of formation, enthalpy of the reaction is negative 91.8. And then we use this equation, delta H surrounding equals negative delta H system over temperature. Negative 91.8 kilojoules, we are converting it to joules. 1000 joules equals 1 kilojoule, and the temperature 298. Okay, so here's the temperature, 298 Kelvin. At 298 Kelvin, that is where the temperature came from, 298. So you divide it by 298. So there is a negative here, and this is also negative. So this negative and this negative will make it positive, 308. So the delta S surrounding is 308. See, delta S universe equals the sum of these two, delta S system and the surrounding. System was given to us negative 197 and the surrounding 308. So delta S universe is 111. So remember we said the entropy of the universe need to be positive in order for a reaction to be spontaneous. Since it's 111, delta S naught universe greater than 0, the reaction is spontaneous. Although the entropy of the system decreases, this is outweighed by the increase in the entropy of the surroundings. Okay, so the reaction is spontaneous. We can see it's the system entropy decreases, but the surrounding entropy overweight by the increase in the entropy of the surroundings. So as a result, it is a spontaneous reaction. Okay. So for a spontaneous reaction, you can have a delta is negative or delta is positive for the system. So this is showing it in the graphical form. System delta S naught is negative, but the surrounding has a higher positive value compared to this one. So as a result, delta S universe is positive, and it is a spontaneous reaction. Delta S and the equilibrium state. For any process approaching equilibrium, remember we learned about the equilibrium. For any process approaching equilibrium, delta S naught universe greater than 0. At equilibrium, there is no further net change, and delta S naught system is balanced by delta S naught surrounding. So the delta S naught system at the equilibrium would be 0. For any process approaching equilibrium, delta S naught universe would be greater than 0. Once it reaches the equilibrium, delta S naught system and the surrounding, they both, when you add it up, become the universe. If this is 0, delta S system equals the delta S naught surrounding in the negative value. Okay, both of these has to be same amount, equal and opposite. When a system reaches equilibrium, neither the forward nor the reverse reaction is spontaneous, so there is no net reaction in either direction. Gibbs free energy. Gibbs free energy symbolizes G combines the enthalpy and entropy of a system. See, this is the free energy, Gibbs free energy, enthalpy and the entropy. G equals H minus Ts. H is the enthalpy, T is the temperature. The free energy change, which is delta G, is a measure of the spontaneity of a process and of the useful energy available from it. If you take the change delta G system equals delta H system minus T delta S at constant temperature. Delta G going to be greater than 0, less than 0 for a spontaneous process, meaning delta G is negative for a spontaneous process. Delta G going to be positive for a non-spontaneous process. Delta G 0 for a process at equilibrium. For a spontaneous process, delta G negative, non-spontaneous delta G positive, delta G 0 for process at equilibrium. Delta G naught reaction can be calculated using the Gibbs equation, which is this one. Delta G naught reaction can also be calculated using values for the standard free energy of formation of the components. Just like we calculated the enthalpy or entropy, you can also calculate delta G naught of a reaction using the free energy of formation of the components. Sum of all the delta G values for the products minus the sum of all the delta G values for the reactants, or Gibbs free energy values. For example, calculating delta G naught from enthalpy and entropy values. Potassium chlorate, oxidizing agent, undergoes a solid state disproportionation reaction when heated. Potassium chlorate giving you potassium perchlorate and potassium chloride. Use delta HF naught enthalpy values and entropy values to calculate delta G naught of the system, which is also the delta G naught of the reaction at 25 degrees for this reaction. To solve for delta G, we need values from appendix. We use delta H formation values to calculate delta H reaction and entropy values to calculate the delta S naught of the reaction. And then we can apply the Gibbs equation. First, we have to calculate the delta H for the reaction. Remember, we use this formula, sum of all the delta H values for the products minus the sum of all the delta H values for the reactants. For the products, 3 moles KClO4 times the delta H values for the KClO4. And another product was 1 mole KCl times the enthalpy values. Subtract 4 moles potassium chlorate times the enthalpy value for the potassium chlorate, and then you do this calculation. So this is our equation, just one reactant, right? 3 times this value, 1 times value of this, 4 times the value of that, and then you do the calculations. So these delta H values should be given to you, negative 144 kilojoules. And similarly, we can calculate the delta S naught reaction. Sum of all the delta S values for the products minus the sum of all the S naught values for the reactants. So taking into consideration the number of moles, products minus reactants, so that is negative 36.8. we found the delta S values, we found the delta H values, then we can use the equation delta G naught system equals delta H naught minus T delta S. So delta H we found negative 144 kilojoules, and this was found in joules per Kelvin. So this one is kilojoules. So we need to convert them into the same form. Okay. Negative 144 kilojoules minus 298 Kelvin. This is the temperature times. After you convert 36.8 joules per Kelvin, you will divide this by 1000 to make it kilojoules. Okay. That will give you this answer after converting into kilojoules. So that's the delta G naught of the system. Okay. That is how you calculate it. So we want to find out the delta G. So what we did was we used delta G equals delta H minus T delta S, and we calculated delta H separately and we calculated delta S separately. Also we can calculate the delta G reaction using the delta G of formation values. Okay. Use delta G naught formation values to calculate delta G naught for the reaction. So for that again we need to know delta G values for these three products minus the reactants. 3 moles KClO4 times the delta G value for the KClO4, which is this value, and then 1 times KCl negative 409.2, and then 4 moles times KClO3 negative 296.3. So when you do that, it's negative 134, and then the other method negative 133. So they are almost identical. So both ways you can do it. Let's stop here.